Okay, so we're going to continue the discussion of finite horizon and infinite horizon, and also uh, indefinite horizon. Okay, so we talked about finite horizon Markov-Decision processes last class. Before I go forward, are there any questions? Yes.
We're not starting the week before the homework's due as of Wednesday or anything, right?
What?
We haven't finished the MVP part. So
As I said, when the stochastic shortest path MDPs are over, which is the indefinite horizon,
okay.
then that's when a week from then,
Okay.
Basically that's when the MDPs are done.
Just want to make sure.
Okay. Other questions? Also, I mentioned to you guys that I set a, I gave a schedule, approximate schedule of the, the topics that we plan to cover, the classes and the topics we expect to cover. I think all the topics are not written yet, but I think the schedule will become more fleshed out as we go forward. The essential idea is that I would try to follow, unless I change too much, I more or less will be following what I did last time. So the videos from the last time are still possible. I think they would still make sense. And I am actually, as I said last time, in the last class, I have started recording these slide videos. If that is of any use to you, you can use them. Of course, you get everything in the class. That's good too. Okay. So that's and then make sure that you go to the class page, the 2013 page, because that will have the information about the actual dates and so on. And I also mentioned a tentative midterm date on that. Okay. Okay. Any other questions? Okay. So we talked about finite horizon Markov-Decision processes, which basically start with this idea of starting with V0 and then continuing on to compute V1 from V0, V2 from V1, and so on. We looked at that, so this is basically, this is how it looks like. I'm just repeating it. You have V0 here. V0 is just the immediate reward of each of the states, and then from V0, what did I do? Okay, I went back. Okay, from V0, I'll get V1, and then basically in doing V1, I consider for a particular state, let's say in this case there are two different actions, and then for each of those actions, I know the states they will get me to. And then once I do that action, I only have 0 time left, and so I will basically take the V0 as the remaining Q value from there onwards. And then using that idea, I compute what do I get if I take the red function, the red action, and then what do I take if I take the yellow action, and then I wrote both the red and yellow actions, the expected values here. Okay, and then I'm taking the max of those and then adding the reward of this particular state. That will give me V1 of that state. Okay, and basically the same way I have to compute V1 for this state, V1 for this state, V1 for this state, and having computed V1 for every one, then I can get to compute V2, then I get to compute V3, and so on. Okay, now how far do I go back? It's the horizon that I have in mind. In this particular case, I have horizon 3, and so I just go 3 steps back. Okay, so basically, then having kept that in mind, so one thing that you want to remember is that we are indeed using the dynamic programming in computing this particular optimal policy, optimal value function from which you compute the optimal policy. The way you're using dynamic programming is that you are using value function to k minus 1 stages to go in computing the value function for k stages to go. So 0 is used to compute 1, 1 is used to compute 2, 2 is used to compute 3, and so on. Okay, this is basically where we are essentially using the Markovness of the Markov-Decision processes. because the value that you can get from a state onwards depends only on how long you have to live from that state, not how you got to that state. Do you see what I'm saying? So that's why if you are computing V8 based on V7, at the time you computed V7, you don't quite know how you would get to this state, a particular state, 7 stages to go. I could have come from this state, I could have come from this state. Irrespective of how I get here, if I get here, then I only get V7 of that state. So value function, 7 stages to go of that state. So that's where the Markov-ness is being used. Okay, so the path doesn't matter. All that matters is, the state. Okay, and then of course, because we have finite horizon, the policy is non-stationary. Policy is non-stationary. Okay. What am I doing? Yeah. Okay, I don't know why we are doing this. Yeah. Okay, and then the computational complexity is interesting because we actually came to this thinking the worst brute force way to do this would be look at all the policies and compare them in terms of their in terms of the value they provide. So each policy corresponds to a value function, a value vector. And you say one policy dominates another policy if its value vector is strictly larger than the other guy's, larger than the other guy's value vector. And one vector is considered to be larger than the other vector if this vector is for each corresponding terms, this vector has a value that's always greater than or equal to this one. And there exists at least one guy for which it's actually strictly greater. Okay, so we basically are and so before we looked at this dynamic programming algorithm, we basically assumed that you would have to do work that is proportional to the number of distinct policies, and the number of distinct policies was quite high, if you remember. How much was the number of distinct policies? It's A power S T. So you had to do something of the order of that. Okay, having set yourself up to this, then it looks like anything else looks good, right? So this is this one is exponential in the number of states. By the way, the n here really is nothing but the number of states. Okay, so if you look at what we are doing, we are essentially doing, if the t is the number of, if t is the horizon, then you do t iterations. And in each iteration, you have n states, or basically s number of states. And you're computing for each state the expectation for A actions. Remember, for every state, you consider all the actions you can do, and for each action, the expected value that you can get back. Right? Okay. And then each expectation takes O(n) time, because you can essentially go to any of the states. These actions can take you to the other states in the next level. Okay. So the total time complexity is that is the t times a times n square, or s square. Okay, which looks great if you are essentially expecting this, because this is exponential in the number of states. It's pretty sucky if you actually realize that any realistic problem, the number of states can be very, very high. So to be polynomial in the number of states is not something that you want to write home about. Do you see what I'm saying? It's in fact, this is something that you want to keep in mind. For those of you again who remember the strips planning from 471, notice that in the case of strips planning, you essentially, let's say you would wind up having v state variables. Okay, if you have v state variables, then you have 2 power v states. And now you are saying essentially that you are polynomial in 2 power v, which means it's exponential in the number of state variables. So the question is, where do you put yourself in? Again, by the way, I hope you understand that computational complexity is always in terms of the input. Okay, So if you think of your input as the number of states, it looks certainly polynomial complexity. If you think of your input as a compact input, which is in terms of the state variables, then the number of states is 2 power v, and polynomial in 2 power v is exponential in v. Okay, you want to keep this in mind. In fact, I know there's a couple of you from operations research, in industrial engineering department here. And one interesting thing is that MDPs actually came from OR community. Okay, Ron Howard called himself an OR guy, okay, operations research guy. He basically, in one interesting difference in the way MDPs got looked at in operations research versus AI, is that in operations research, people think that they'll take a problem, spend a lot of time carefully deciding what's the least number of states we can get away with. So they will come up with a representation for the problem such that the number of states is very small. And so if it's polynomial in the number of states, it's not too bad. Okay, in AI, we tend to look at, first of all, people tend to essentially allow generalized representations. So you might have, for example, large number of irrelevant state variables. So for example, picking the right state representation means figuring out exactly what aspects of the problem are relevant and what are not relevant, and making sure that you remove all the irrelevant stuff yourself, you the human who modeled the problem. By doing this, you can make the number of states very small, and then it's only polynomial in that. AI people tend to look at the they use the same model, but they tend to assume that we look for generalized representations where we throw in all the state variables that we know. Some of them are relevant, some are irrelevant. You are supposed to figure out what is relevant, what's irrelevant. You being the intelligent agent. Okay, now if I basically then, so let's say I'll just throw in the same 10,000 state variables for everybody, or same 100 state variables for everybody. In which case suddenly now I'm talking about 2 power 100 states. And now I'm talking about polynomial in the 2 power 100 states. All of a sudden it doesn't look all that good. It's the same complexity result. AI people look at this and see, oh my God, what a sad story. And OR people will look at it and say, that's pretty nice. It's polynomial. You see what I'm saying? It's a question of what kind of problems you're trying to solve and how much human effort is being put into, modeling the problem. Here's another interesting point to keep in mind since I've gotten into this OR versus AI thing. OR, operations research people, essentially sell employees. They train students and they say, you hire our students, our student will listen to your problem, figure out what's the best way to model it, either for MDP or for digital programming or whatever else. These things are such big things that normal people cannot touch them, highly, these are caricatures of course. Highly trained PhD, MS students will be able to help you. That's the model with which operations research works. So it's reasonable that you're paying money to somebody and they'll spend a lot of time figuring out what's the smallest state space that you can get away with. AI people, of course, are essentially cutting the branch they're sitting on because we are trying to automate everything. Right? We don't sell employees, we sell technology. We sell technology which eventually remove the need for employees. So that's why, in essence, you are essentially coming up with, anybody should be able to write models for MDPs. And they are likely to write bad models. And so they're likely to have very large sized models. And then, so we would spend a lot of time on figuring out how to essentially automatically figure out, and automatically reduce the state space sizes. Okay. Anyway, but the same problem has been, looked at from two different directions. It's that mathematically it's exactly the same problem. It's a question of what do you want to do with it. Okay. So anyway, so this is a polynomial result. It looks kind of good, okay, but it's really exponential result from the point of view of state variables. The complexity is exponential, not polynomial, from the state variables point of view. Yes.
Why is that a square?
Because you have n states and each state's expectation takes n. For each state, you are considering all the actions and those actions are going into all possible states. Okay. So that's basically the value iteration for finite horizon MDPs. And when if you compute this MDP by this backward dynamic programming, then you will get the optimal policy. Yeah.
But the number can be larger than n squared.
What?
The previous thing, the n
Mhm.
squared, number can be larger than.
What does it mean? What number?
You're restricting to the n square value.
No, n is the number of states.
Yeah. So why square of it?
This is basically, so this is your reasoning, right? There are t iterations. Under each iterations, at each of the n states, you need to compute the expectation. The expectation computation itself takes order n time. Okay? That's what you need to convince yourself. This is only a worst case complexity. It's not average case, it's not the optimized, it's a worst case complexity. Okay, so then you have, basically, you have to convince yourself that, what we are doing in this case does give you the optimal policy. I mean, by construction, it should be reasonably obvious that we are getting optimal policy of k stages to go. Okay, and then one other thing that you want to remember is the optimal value function is unique, but optimal policy is not unique. Okay, because multiple policies might wind up going to the same value function. Now, if you remember, I think I may have mentioned this last time too, but if you remember one of the examples that we had originally, as you keep changing the reward function, you get different behaviors. In one case, we basically said the value, the action in each state can be any of the four. If you say the action in a particular state can be any of the four, they're all equally good. That means you are essentially talking about four possible policies. Do you understand what I'm saying? If it turns out that there are huge number of states in one particular state, in the optimal policy, it doesn't really matter which action you do. Okay, in which case essentially there are four optimal policies. I mean, if there are four actions. Okay, that's why the number of policies is so the value function is optimal. So value function is unique, but the policies are not unique. In fact, there is this interesting connection between policy values and policies, value function and policy, and you keep seeing this. In a minute, actually, we'll get to the policy iteration algorithm where we actually wind up using this. So given a value function, you can convert it into a policy by taking greedy policy. Right? We talked about it last time. Given any value function, you can compute the greedy policy, which is basically saying for each state, pick the action that according to this value function would be the best action. To do that, you compute the expected value for each of the actions from this state and pick the max. That would be the greedy policy. Remember this whole thing about exploration, exploitation that we discussed last time? Okay. So given any value function, there's a greedy policy. Now what's interesting is that if you given a policy, you can compute the value function. This becomes even clearer as we go to the infinite horizon MDP. So because of this non-uniqueness, because multiple policies might correspond to the same value function, for example, it turns out that you can start from a value function, you can compute the greedy policy, and given that policy, compute the value, and that will be a new value function now. Okay, with respect to which now you compute the policy, and you can compute the value, and if you do this, you're going from policy to policy to policy. And that's the policy iteration algorithm. We'll get to it in detail in a minute. The only thing, of course, is are there a specific value policy function such that they are essentially connected to each other? That means you go from value, you get to the policy, and then you go from that policy, you go back to the same value. That will only happen at the V star and pi star. If in fact, our policy is the optimal policy is unique, then given V star, the greedy policy with respect to V star is pi star. And the value function of pi star is V star. Only there it is fixed point. Up until then, you can actually jump from one value to a policy to its value to its policy to its value to its policy until you reach V star pi star. That's what actually happens in the policy iteration algorithm. Okay. But policy iteration doesn't make sense for finite horizon mark validation processes. It actually, we'll talk about it with respect to infinite horizon mark validation processes. Okay. Now so this is all the discussion I'm going to do about finite horizon. Are there any further questions on this stuff? Okay. So next we are talking about infinite horizon. We already talked about it last time, but I'm just going to go through it quickly once. So you are now considering situation where there is no bound on the horizon. So the horizon is infinite. So you can live infinitely long. You can do infinite number of actions. So, and to do that, basically to even support the definition of a reasonable optimal policy in that case, you want to make sure that the value of a state is not going to become infinite. Value of a state with respect to a policy doesn't become infinite. Okay. First of all, you realize that the moment you are infinite horizon, as we talked about from the last couple of classes, you will only have a stationary policy for an infinite horizon MDB, because it does not make sense to talk about finite or non-stationary policy. Because it's always, the number of steps you have left to go is always infinite. Even if you lived billion years, you still have billion more, infinite number of years to go. If you assume you had infinite number of years to begin with, right? Infinite number of epochs to begin with. Okay, so there's only, we're talking about a finite, we're talking about a stationary policy, and we also want to make sure that given an arbitrary policy, it's not going to give infinite values to all the states. If it does, then there is no notion of optimal policy, because every random policy will be having infinities all over the states, and so all of them are equally good at that. Right? To avoid that, one trick that we basically do is we essentially discount future rewards with respect to the current state, and that's what we are doing here. So you essentially take expectation not of just the sum of the rewards, but expectation of discounted rewards, expectation of the sum of the